All right. Hello, everyone. My name is Fotis. Thank you for coming here today. As I said, I'm going to talk about PyTorch, what it is, how we can use it, and just the general idea here is to give you an idea of what it is in case that you want to work on that. It's not an extensive tutorial. I'm just going to show you some of its features, and with the hope that it can be like a starting point for everyone that wants to start working with neural networks or more practical applications. A small chance that we're gonna do a more advanced one, but it's gonna be a lot later, like the winter semester or something. All right, so from groundwork to practical deployments, we're gonna try to understand what tensors are, operations of tensors, network architectures, and some training techniques. As I said, my name is Fotis. I'm a PhD student with the chair of cyber-physical systems. A small outline. So we're gonna start with an introduction of what PyTorch is. We're gonna talk about the basics of tensors, what they are and why they're important for PyTorch, and how they enable PyTorch to be a popular library. How to build neural networks, how to train them, and some practical applications on PyTorch. We're not gonna go too deep in the advanced topics. We're gonna see a few like fine-tuning or transfer learning, and then at the end we're gonna wrap up and we can discuss anything that you want to discuss. All right, so what is PyTorch? PyTorch is an open source machine learning library for Python. It provides tensor computation with strong GPU acceleration, and which is really important, especially when you have to do that many calculations as you need to do in neural networks and general machine learning. It enables us to build deep neural networks with a built-in tape-based autograph system, so you don't have to care about writing all the equations for taking the derivatives of every function that you need to implement, or at least the most common ones. And it's highly interactive and user-friendly. Let's dip a bit deeper into the important modules of PyTorch. First of all, we have the tensors. That's one of its modules. It's similar to NumPy's arrays, but with GPU support. We have the AutoCRUD, which helps us which simplifies the training and designing of computational graphs. We have the neural network module, which is the base class for all neural network components. The Optim, which is for to implementing various optimizational algorithms used for training neural networks. And something that is not here is also like the Torch Vision module, which, at least for me, which I'm a vision guy, provides data sets, model architectures, and image transformations already, so you don't need to implement them if you want to have a kickstart really quickly. Okay, so a fair question would be, why use PyTorch for deep learning? Why not just use NumPy or I don't know, any other tool? First of all, we have the dynamic computation graphs, which gives us flexibility during model building. It has a Pythonic nature, so PyTorch syntax and usage is similar to Python, making it a lot easier to use. It has one of the most important things: strong GPU acceleration, as we did, which speeds up computations and makes it feasible to work with large data sets. Industry adoption is really important, used by many companies and research communities and production. And the community and the ecosystem around PyTorch is really strong. It's supported by a growing community. ample learning resources and tools for visualization, model serving, etc. That's just a few that I showed there of the tools that you can work with PyTorch. All right, any questions so far about PyTorch? Okay. If, yeah, please.
Why should you use PyTorch instead of Tensor?
Basically, it's like with a few words, it's how much flexibility you want to have. TensorFlow, from I don't know since when, it also has kernels inside, so it's really fast if you want to have quick implementations and lightweight implementations, most probably. There's also PyTorch Lightning that it's get messy. It really depends on what you want to build for research, and if you want to be flexible enough, PyTorch is the go-to. Okay, let's deep into tensors. So, what are tensors? Tensors are fundamental to machine learning and deep learning. They're mathematical entities that exist in a structure, interact with other entities. That's practically how you instantiate all the multiplications needed for the neural networks. It can be scalars, can be vectors, can be matrices, which all of these are special case of tensors. They can be more than that. It can be more complex than that. It can be matrices of matrices, for example. Let's have a look. So a scalar is a zero-dimensional tensor, just a single number. A vector is a one-dimensional tensor, so an array of numbers, and a matrix is a two-dimensional tensor with 2 degrees of numbers. And as you can see in the picture, then we can go even more complicated than that, and we can have like a matrix of vectors, we can have a matrix of matrices, and so on. So what are the key attributes of a tensor? Number of axes. So here, this whole thing on the right of your screen, the purple and the green thing is all one tensor. And it has 4 axes. One axis is here, so it's like 2 dimensions here. Another axis is this one, is 3 dimensions, and here's the same 3. 4 here and 5 there, which is also its rank. The shape is this thing here, is 3, 2, 4, 5, and it's a table of integers indicating dimensions along each axis. So we tell this in the first axis it's 2 dimensions, the second axis is 3, 4, and 5. And final thing is the data type, the type of data contained in the tensor. In this case, we only have integers. Okay, why tensors are important for neural networks? They support automatic differentiation. It simplifies the model implementation and gradient computation. In terms of scalability and batch processing, it enables efficient processing of large data sets, data batches. So in general, like tensors are the building block of the neural networks in PyTorch, and it's what it enables the automatic differentiation and the GPU acceleration. Okay, and with that, we can move to the more programming parts of this tutorial. We were gonna see the tensor basics, so I'm just gonna give you an overview here, creating and manipulating tensors in PyTorch. That is, we're gonna create tensors, manipulate the tensors, do some mathematical operations on them, reshape them, and see how autograd works. So if you have a laptop, if you want to write along with me, you can open your Google Colab if you want, or if you have an already installed version of Jupyter Notebook. I said Google Colab in the email because I think it's easier to get started. It has everything installed already, so you don't need to care about independence or whatever. Okay, so let's jump in. what you will need to do for this tutorial is to enable the GPU acceleration. So it should be Python 3 here, the runtime. So let me show you again. So we go to Edit, Notebook Settings, and in the hardware accelerator, if you haven't changed it, it will be none in the beginning. So just choose GPU and leave a GPU type or whatever. So it's the free version, so it will only give you T4. You just do save. It will start connect here. And that's a small code to just check that we have CUDA. So we're just importing PyTorch here. And then we just ask if CUDA is available. All right, so with that, let's start. So if you want to go to create a new code cell, you either go just here and you press code, or as it also says, you can do Control plus M plus B to create a new one. Let's create our first tensor then. Let me change to English because I'm more familiar with that. So torch.tensor and for Shift and enter, or you just press here T1, and we just created a tensor. That's our scalar tensor. Let's create another tensor with more dimensions. Let's make it a vector tensor. 1, 2. Is it big enough for everybody to see? No. Let's see. What about now? So 1 to 4. Let's call that T2. But in Lygerakis, you have to give it as an array. Here it is. Then we do the same. If you want to create a matrix, then we have to create vectors of a vector of vectors. So let's say we have 5, 6, 9, 10. I think I have one more parenthesis here. Yep. So here's our matrix, and finally let's create a bit more complex tensor. Gonna call that T4. Yeah, I'm just gonna copy paste it. So here again we have a vector. Actually, let's start from here. We have a vector of vectors of vectors. And why we need tensors that are so complicated? It's because inside neural networks we have a lot of dimensions. We have things multiplying with other things. We have different inputs. You can have an input that has 20, 30 dimensions and needs need to be multiplied again and again. And that's pretty much how you create tensors. Let's have a look in their shape. As we said, it's one of the important the key attributes on it. So T1 shape. So you see the first has just a scalar. The second one has four dimensions in the one axis. This one has two axes. The one has 3 dimensions. The other has 2, and so on. All right. Let's get our hands dirty and start playing with these tensors. Let's add two to T3. And I should remind you that T3 is like this tensor here, 5, 6, 7, 8, 9, 10. So we just add 2 to everyone. If you just add 2 here. If you multiply, we'll multiply with every element again. So we can do matrix multiplication. So this time I'm gonna use T3 again. I'm gonna use at. To do matrix multiplication, is there any question there? No? Okay. We're to do matrix multiplication, we're just taking our matrix T3 and we're gonna multiply it with, let's create a new tensor with the same dimensions. All right, just hope I'm not too loud for the people in the front row. That should be right. No, I think we need one more dimension here. Yeah, because it's torch dot tensor. We are missing something, I think a comma here, right? There you go. So we multiplied T3 with this tensor here using the at symbol. We can also, let's create a new tensor called T5. It has one, which is matrix, and let's add it to T3. So if you remember previously, when we added 2 to T3, it just added 2 everywhere. Now if we add T5, it's just gonna go to every dimension and add the corresponding value. Yep. Why? Now it's gonna be element wise. Here that's not element wise. Here is element wise. So if you also had like T4 here, let's do it like T5. It will multiply like 5 times 1, 6 times 2, it's 12, and so on. So we'll take every element. Okay, and lastly, let's also see how we can reshape a tensor. Print, and again, it's the Pythonic nature of TensorFlow. We just call reshape. And it changes the shape of the whole tensor. Yep.
Maybe one more question. Does it matter here where your arrays come from? Could you just take any number?
Where the what?
If you have any NumPy and D array, could you use those as well to make a tensor out of it?
Yes, you can. But you have to convert first. You cannot multiply a tensor with NumPy array. You have to convert either from tensor to NumPy or from NumPy to tensor.
Okay, and so this torch wrapper is just so PyTorch knows what it's supposed to do.
I didn't get your question.
So could I use a normal NumPy and D array also and put it into PyTorch, or does it need this?
Yeah, you have to convert it to a tensor first, and then to do multiplication to use all the benefits of TensorFlow.
Okay.
Pretty much, these are like the same operations that you can do in NumPy. Like this operator, everything, like it's the same in NumPy. Okay, let's dip into tensor gradients. So, in general, if you're not familiar with Jupyter notebooks, you can also like add text. So let's say that tensor gradients, and you can do more fancy stuff, whatever. Okay, let's get a T6 tensor, new tensor, has 1, 2, 3 axes, and let's also create a weight matrix. Let's call it W. Torch tensor. And that has points 1, 2, 3, and 4. And we have to specify that here grad is required. We do the same with a bias vector. Oh, come on. And here I think we need less dimensions. We need to here. Okay. And let's do a standard multiplication for the perceptron. Let's compute. That's without activation, at least for now. Let's do a multiplication with T6. Let's say that's our input. Let's add the bias. Oops. And print Y. So this is what Y is. It did all the matrix multiplication here and added the bias, and you also get the information that we have to this has to also have to compute the gradients at the same time. So that was it. If you just say that it requires grid, then the computational graph is already done by now. So we can go and ask to do a backward pass. And let's say that our like error or just fake error. Once like. It's okay. Yeah. And that will take the dimensions of the shape of y and create ones like that. We'll pass it backward and let's find the gradients of, yeah, let's see first w. That's how you access the gradients. And here are all the gradients for w and for b. And that would conclude the tensor basics. Does anyone have any question on that before we move forward to a bit more, I wouldn't say complicated, but yeah. Yes, please.
The dots after the integers, sometimes there's a dot, sometimes nothing in code.
Mm-hmm.
What does this do?
The dot tells you, actually, let's find out. T6 has dots here. It technically creates, if you only have clear numbers with no dots. Oh, it's still a float. Yeah, maybe took it from previously, but in general, like if you put the dot, it means that it's gonna treat them as a float. If don't, it's gonna be an integer. Oh, yep.
So what is the gradient, which is the calculator?
What is the what?
Gradient.
The gradient?
Yes.
These are the gradients for W, and this is for B.
What's the formula for it? Like what is the definition of the gradient which is calculated?
It's you.
Is this the partial derivative of y at b?
Yeah, it's a partial derivative of y with respect to W and then with respect to B. B and W being tensors, they carry like whatever you ask to be the gradient with respect to, it's gonna be with respect to itself. So W carries its own gradients and B is carrying its own gradients. Here, like we only have the error comes from Y, but it can be cascaded in the neural network and can come from the previous layer. Any more questions? All right. Okay, so moving forward, let's see how we can build and train neural networks in PyTorch. And in a nutshell, I'm going to define a neural network in PyTorch, train neural network, define a loss function, backpropagate and use an optimizer, and set up a training loop. Okay. So for that, we're gonna need first to import the neural network module from PyTorch and start creating, let's put it alone, and start creating a class that's gonna host our symbol net. Yeah, it's gonna inherit from module. So for the initialization, we're gonna eat the input dimension. We're gonna need a hidden dimension. and an output dimension. Okay, so our input layer, gonna call it FC from fully connected. Let's call it 1. And in the neural network module, we have the linear layer. And I'm gonna give it the input dimension and then the output dimension of it. It's gonna be the hidden. So first layer is done. And then we need an activation function. Let's use rel here. It's with capital. And then we need an output layer. We're gonna call it FC2. Again, it's gonna be linear, but this time I'm gonna take the hidden dimension and convert to the output dimension. All right, so we have created a bunch of layers, a couple of layers actually, and now we need to combine them together to create the neural network. So we're gonna need to create a forward function. Forward. Yeah, we need the input here too. And it's a class. So X is the input. So let's pass it first from the first layer. Then we need the activation. And then we're gonna put it through the last layer. FC2. And we need to return that. All right, that was it. Just create our first neural network. Let's test it. Okay, so input dimension is gonna be 10. We have a dataset for that. Yes, I do later. So the dataset we're gonna give it to it is gonna have an input dimension of 10. Let's create a hidden layer of 20, and the output is gonna be 1. A nice thing to see if to debug, because here it's easy, but if you have a bunch of things happening here, it's good to print the network and see how is it structured. So it goes from up to down, from input to output, and every line goes as input to the next one. Everything is great. We also have bias. You can avoid it if you want to. It depends on the application. Usually just don't care about it. All right. Now, let's create some dummy data. So as a lot of you may have guessed, PyTorch is using on the backend NumPy because it's using all of its functions. So if you want to create a random number, you just do random. Whoops. And it's gonna be 10 times 10. Let's create some labels for them. Torch dot tensor. So we're gonna create a tensor. Just only needed to be a vector. So 1, 0. Oh, come on. I'm just putting random labels here. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. One more, 10. There we go. And they need to be float. Not here. There. We need a criterion to fit. Criterion. So here we're gonna use the binary cross entropy with loaded loss. We need an optimizer, so let's use CGD, classic one. So we go to the optim module to get that. CGD, there it is. And we're gonna give it the network parameters. And we're gonna give it a learning rate of 0.01. All right, and we have the criterion, we have the optimizer, we have a neural network. Now the only thing that is missing is to create the training loop. So let's say we're gonna train for, I don't know, like a small network. Yeah, let's do 5 epochs. So 4 epoch in range epochs. First, we need to bring to 0 all gradients of the optimizer. So optimizer it was 0 grad. Then we need to create a forward pass from the network. Oh no, input data, wasn't it? Where is it? Yeah, just input. So that's the forward pass. And so let's say that we do that once, so you have an idea what the output will be. So here, after the multiplications, it's gonna have 2 axes, 1, 2. To make our life easier and discard the inner, so each module is like one tensor here inside. We want to discard these inner square brackets. So to do that, we're gonna use this first here. That's the output width, and that's as with using squeeze. So squeeze is gonna get rid all of the intermediate square brackets. So we're gonna use that here. Because also our tensor, our labels here are, they should be the same dimension, so we can like take the difference between them two. To calculate the loss, we're gonna use our criterion. Output labels. So we have our loss, and now it's time to do a backward on our loss to compute all the gradients. And then do a step on the optimizer. That will take the backward loss that we have calculated and will put it back into the weights to update them using the learning rate that we have set, or if we have a more complex optimizer like ADAM, whatever learning rate it has for every weight. Okay, then I'm gonna steal and write this code here. So if for every 10 epochs, let's put that at 100. So usually you put like a printing function every now and then to do some stuff, to save your model or whatever, to see where your loss is. And let's run it. Of course I have something wrong. It should be parentheses here. Yeah. What's wrong here? Target size must be the same as input size, but we have squeezed it already, haven't we?
Output is equal to output dot squeeze.
Sorry?
Output is equal to output dot squeeze.
You're right. Thanks for pointing out. I was fast because this is a really simple neural network, and you see that the loss is decreasing eventually. That was probably the simplest neural network that you can write, and probably the most useless one. So I'm gonna set it here if you want to fill up the code, and we can move with a bit more complex and more like real world applications. All right. So if everybody's done, let's move forward and see some practical PyTorch applications. We're gonna do an image classification. We're gonna perform an image classification task with a fully connected neural network. We're gonna see how we can, what is the difference between just using it on CPU, because right now we're just training on CPU. How we can train on GPU, and how image classification is different with CNNs. I'm gonna do transfer learning and see how we can save and load trained models, and about data parallelism. Okay, but before I jump into that, do you have any questions about the code that we saw already? Okay. Just stop me whenever you want to explain things. All right, so moving forward, we're gonna need to import a bunch of things. So I'm gonna put them here. Some of them we have already imported. Some not. This matplotlib to plot the dataset. We're gonna need the data loader to put the dataset inside, and it helps us with batches and doing transformations and everything. We're gonna work on the MNIST dataset. You're gonna see how it looks like. Transformations. That's especially for me that I'm doing vision. That's one of my favorite libraries to get started with vision data sets, and we want to test something, some model or whatever. We're importing the ADAM here, optimizer, some random split, and we're gonna see everything on action. So first of all, we need to download the training data. We'll do it automatically. It's MNIST here. Can we go inside? No. Yeah, because I haven't run this. Anyway, so root tells you where to put the data. So it should be no here. Here it is. CSV, null them. And it also has a train argument to tell you if you want the training part of the data set or the test one. If you want to download it and what transforms, here we're just gonna convert that to Tensor directly. This code is publicly available on GitHub, so I'm gonna give you the links and everything at the end of the presentation. Yeah, I think I have already downloaded it. Yeah. And okay, then we need to put these data sets into a data loader. So first we give the data anyway, whatever kind of data we have. We specify the batch size. Let's put 64 here, and if we want them to be shuffled or not. I'm gonna do the same for the test. What again? Data loader is not defined. Why not? Yeah, because I did a typo. It's with a capital L. Okay, that's a small code to just visualize. You don't need to write that. Just to visualize what we have imported. What is the data set? Let me zoom out a little bit. So it's 100 digits. Their size. So you see the batch dimensions here. There are 64. That's the first batch. And the dimensions, they're grayscale, so you don't need the third dimension, like a fifth dimension here to describe also the RGB. And they are 28 by 28 pixels. And labels are just like exact numbers, 0, 1, 3, whatever they are. So the task here is to, when our network looks at an image, these are 64, aren't they? No. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there's 64 here. So when they see like a bunch of it, it knows how to classify all of them. All right. So let's steal the implementation of our simple network from the previous exercise. Here we're gonna need a bit more complex. Actually, I'm gonna just copy paste the structure here. We need a fully connected layer for sure. Gonna be, yep. Oh yeah, sorry, forget. linear, and that's 28 by 28 by 28. And the hidden dimension is gonna be 512. So what we're gonna do for the image, let's say we have these images here. That's a 9 pixel image. What we're gonna do is to just flatten it out. 2, 3, 4, 5, 6, 7, 8, 9. We're gonna convert the image to that so we can like give it to a full connect layer and do the multiplications from thereafter. So we need another, let's put another fully connected layer that gets us from 512 dimensions to 512 again. And the last one is the output, which is gonna get us to 10 dimensions. So it's gonna be one hot vector at the end. Will tell us, not one hot vector, sorry. It's gonna tell us from 0 to 9, what is the probability of being that digit. So we also need a ReLU. And what activation function should I use here? Yep. I think it's the most popular activation function, at least for the output layer. So for those who don't know the softmax activation function, or in general the function, it just gives you the probability of its class. It's positive what it gives you, and it sums up to 1, which is what consists of a probability. And yeah, no. Softmax, and we want it to be only have 1 dimension. That's all. Let's define the forward function. Forward, and then you know the game from previously. We need, first of all, we need to do this operation here. So we're gonna view our input. -1 gives you whatever dimension is left. So you can use it in 1 dimension when you use it, but only 1. 28 by 28. And so first we need to put X into the first layer and then put that into the ReLU. So it's gonna be encapsulated. We're gonna do the same for the second layer, but in the third, which is the output layer, we're gonna use our softmax. And we're gonna return the result. Why don't you like it? Because this is, yeah. And yeah, here, semicolon. Thanks for pointing out. Let's run that. Okay. Not to bother you too much. First of all, we're gonna need to import time function. We're gonna see why. We're gonna count how long it takes per epoch for the model to pass. So I'm gonna instantiate our model. Let's run that. So you see that we check the device here and it's running on CPU. Again, we're going to create our optimizer. This time, because we have probabilities, we're going to use the gross entropy loss. I'm going to define epochs to 5, which is going to be a lot because that's a big network. And then it starts to become slow, especially if you have a cloud machine. So for each epoch in the region of epochs, we're going to start a timer here. And then we need to iterate over our data set. So I'm going to get the batch ID. So if you, do I need the batch ID here? Anyway, so enumerate here will give you the batch ID, like how many batches there's in the data set, given that we have 64 batch size. Train data loader, any kind of data loader, will give you the data and the target as they are in the data set if you iterate to them. So the first time is going to give the first batch, second batch, and so on. Okay, again, you know the drill from the previous network. We need to set the optimizer gradients to 0. If you don't, they're just gonna accumulate over time. So the first time they're gonna pass, it's gonna have like it starts from 0, but then like it adds up, it adds up, it adds up. If you don't clear it, it will like keep adding up. So forward pass, computing the loss function between the output and the actual targets, backpropagating the loss, and then we're gonna do a step in the optimizer. I'm not faster than copy pasting. And just so if the batch ID every 200, we're gonna print the epoch, batch ID, the length of the data set, and the loss. Item here gives you the value that's in the loss. It's a tensor, so it will keep printing the whole tensor thing that we saw previously. With the item, it will only print the value of it. And that's per batch, and per epoch should be somewhere there. Just gonna see how long it takes for every epoch to run. So how long the network takes to process the whole data set. What don't you like? There you go. Let's run it. So as you see, it takes a long, even for an epoch now, because we have MNIST has 50,000 samples in the training data set and 10,000 in the test. So it will take some, you see here that for an epoch it takes 20 seconds and so on. Let's see another epoch, how long it takes. And let's see how we can like do it faster. So until it's training, any questions so far? Yep.
Back to the acceleration check. As you look at it, I think
Where?
model is simple net, and then I think check for the.
Here?
No, I think a little bit below. Yeah, check device of the model. Okay. What does this do? Check device of the model.
Check where the model is, where the calculations of the model is going to happen. And here it's on CPU. That's why it's so slow right now.
Okay, thank you.
Before trying to fix that, and while that's training, let's see how we can test the model. So first of all, we're gonna use the .eval method, which it's gonna stop calculating gradients. And if you want to go back to training, you have to call .train again. Setting test loss and correct answers to 0, and then starts with using torch no grad. It will also not compute any gradient. And then we're just iterating through the test data loader. We're passing, we're doing a forward pass on the data, and we accumulate the loss over the data set, how many predictions were correct or not, and then we're just printing it. Is it finished? Yeah, it's finished. So let's see how well the model does. 10%, not that great. Let's start fixing things. First of all, let's put the model in the GPU. You know, that's why we're talking and we're having this tutorial, that we can use the GPU acceleration. So first you check. We have checked that we have CUDA previously, like before we start the whole tutorial. Otherwise, it wouldn't make any sense. Here it checks if CUDA is available. If not, we'll use CPU and put it in the device. So in the device we have a CUDA, and let's run the code again. Oh no, wait, I didn't send the model. So to send the model to device, we have to go back here, and you just add 2 and the device that you want to send it to. That's not gonna be enough, as you're gonna see. It's gonna complain here. Any idea why? That's because right now the model is in the GPU, but the data are still in CPU. So what we need to do, and what's a common problem usually, is to go here. Let's see which ones at once. Target, data, target, and send them to device. So now both the data and the model are on the same device, and they can train, like all the calculations can happen. You see it's a bit faster. So from 20 seconds we're down to 12. In seconds it doesn't look that, but you can like cut in half. Like from a day of training can be like 12 hours of training, and that's a lot. And there are like many tricks that you can optimize and make things faster, but we will talk it probably in another tutorial. Okay. Evaluation is going to be the same because we're training exactly the same model. Okay, so this also needs to be to device, and yeah, the data also need to be to the device. Oh, okay, even worse accuracy now. But why? What is the problem here? The problem is that images has positional information. They have structure, they have patterns, which when we flatten them out, we break these patterns. So it's information that we not get used to. We cannot make use of, I'm sorry, we cannot make use of these information. So what we're gonna do is to create a CNN. I promise it's not gonna be too long, so that's why I'm not making a break now. It's think top's gonna make another. It's gonna take another 10 minutes. So what we need is to create a new network. Right now with convolutional layers. So the first two layers are gonna be convolutional, and the second two is gonna be linear. So the first convolution layer, we start from 1 because that's we have black and white images, and that's the dimensionality of the layer 32. We go from 32 to 64. The kernel size is 3. Stride and padding is if let's say that you have 28 and you move your filter, and if the filter at some point gets here, for example, you just pad everything else with 0 or 1. And the stride is how many empty pixels you. So if we have a stride of 1, let's add a bit more. And you have a kernel of 3. That means that you will multiply with 3. You're gonna calculate. You're gonna do the multiplications with leaving 1 between every pixel. So instead of being here, it's like it takes a bigger space, the kernel. And then from whole here, it moves to the next one, and so on. So first layer, second layer, and then we're doing a max pool layer. It's going to reducing the dimensionality of the layer that you're inputting. So here we have a kernel size of 2. Max pooling, it means that we have a kernel of 2. It will take a kernel and put it on the image, and whatever is the maximum value will give it to everything. Sorry, it will take the maximum value, will create a new picture which has less pixels. So instead of 4, you're gonna have 1. You're gonna keep the biggest. That's a classic method to reducing the size, because all these multiplications are creating bigger bigger features. And then we're just gonna have 2 layers. It's gonna be taken with the classifier. So up the convolutional layers are learning the features, and then the linear ones are classifying it. Again, we're gonna use the rel in the between and the softmax function in the output. We're putting everything in the order I just described. Let me run that. And then it's technically the same iteration function we had previously. We sent the model to the device. We're starting with the ADAM. We're initializing the ADAM optimizer. We're using cross entropy loss. It's pretty much the same. Let's train the model and see if we can get a better accuracy this time. It takes some time. There you are. I see the loss here is not dropping too much. I'm not sure what's the problem, why it's not dropping. Anyway, until we wait, let's move to the last part that I would like you to see today, is how we can do transfer learning. Transfer learning is when you have a model trained on some bigger and general data set, and then you try to leverage this knowledge that the model has to more specific task with a more smaller data set and more task specific data set. So for that, we're gonna import the Torch, the models from Torch Vision. Our model is gonna be the ResNet 18 model pre-trained, and calling that, it will download the weights and put them directly in the ResNet, so it's gonna be pre-trained. What we're gonna do then is to freeze these weights because we don't want to mess around with them. They're already trained, so we will put for all the parameters, we're gonna put requires grad to false. We're gonna change the first layer because here we have we don't have RGB input, we only have black and white input grayscale, so we need to change the first layer to be compatible with our input, and then the output also needs to be changed, because as far as I know, ResNet is trained on ImageNet and it has like 1,000 labels, if not mistaken, and we just train it as a simple network after that. So as you see, it downloads the weights. You see now the loss is a lot better. It starts a lot better because we have a pre-trained model that knows a lot better how to extract these features that are in the images. In general, it's an overkill to use ResNet on MNIST dataset. MNIST dataset is quite easy, so even our custom classifier is sufficient. In general, you see the loss is like super low right now. And the final thing I would like to discuss with you is how we can save this model and use them furthermore. You just it's the save function. You give the model the state dictionary, so it will give what are the weights, the biases, everything in the model, and here's the name that you can give it to it. To load it, it's exactly the load state dictionary function, and sorry, for the load you just need the path to wherever the weights are, and these weights you need to incorporate them into the state dictionary of the model. Now, in any case, in the case that you have multiple GPUs and you want to run faster your code even more faster, and your training, there is this data parallel model, which is probably the most efficient way to do parallelism. What it does is, if you have two GPUs, it will copy your network into both GPUs. It will split the data set into both GPUs, so it's going to be half the time, plus minus some overhead to do all this operation. It will compute the gradients. It will merge them together from the two GPUs and going to update two networks. So at every given moment, you have the same network in both GPUs, but they're splitting the data in the order of the GPUs you have. Here we only are giving one GPU, so not gonna make any difference. Actually, it's gonna be less because the overhead it will try to do to impose on that. Okay, let's evaluate our model now, since it has finished. Where is the evaluation? Here it is. Please be better. Yeah, 88% is better. So, to wrap it up, Sorry. Oh, I have a pointer too. So tensors are foundational to machine learning and deep learning, enabling efficient computation and encapsulation of complex data structures. PyTorch leverages tensors, as we said, to be able to, both for the computational graph, the efficient, flexible, user-friendly interface. We can use it for building and training neural networks. Its features, the features that it provides is that we can design complex models, take advantage of modern hardware accelerators, GPUs, TPUs, whatever we have. Thank you for your attention. If you have any questions, please let me know. Here's my email. I also have included the link to this presentation. You can find the code in my GitHub and or through this presentation. So if you go back here, you'll get directly to the code, and I have comments and everything. So whatever, like I was talking over the code, it will be there. Checking the device and everything, for example. If you have more questions, I'll be more than happy to answer them.